All right, so hello. In this video, I am going to do an end-to-end binary classification analysis using Python, in particular, scikit-learn, and some of the libraries or some of the functionality available in that library. Of course, that is just one very, very small slice of that ecosystem, but it is a very popular um, library for binary classification, and I do think that there's a lot of value in that. We can use that one library and the functions, methods, estimators available in that to kind of demonstrate that process end to end. One thing I'm going to do before we get started, I want to open up just an incognito window. I'm going to go out to GitHub, and when you're there, if you will search user Freeman Analytics, you'll be taken to the repo for Freeman Analytics. And then if you look, we've got Python analysis examples. And in particular, I've already posted the notebook or a completed version of the notebook that I'll kind of be going over today in this binary classification diabetes. So you'll have the data set and you'll have the notebook and one of the plots that are going to be generated. So in particular, the data we're going to be using is this diabetes underscore prediction underscore dataset. And if you pull up that notebook, you will see I did put a link to where I got the dataset. So this is just a Kaggle dataset. So if I open that link in a new tab, it will take you to the Kaggle repository where I got that CSV from. And I do believe that this is a fabricated data set. They make no mention of, this being tied to, an actual population. And I do believe that, the number of rows and whatnot, if I'm not mistaken, is it's like exactly 100,000 or so forth. So, it might very well be, some type of a synthetic or simulated data set, but nonetheless, it's going to do the job for showing, allowing us to do what we need to do to demonstrate a binary classifier. All right, so if you'll make sure you've got that data set down, I've got this demo folder on my desktop, and that is where that data set lives. And then I have got a completed version of that notebook that I'm going to be kind of referring to just to make sure that I don't get off too far off base. I'm going to, again, just kind of use it as North Star. But I will be demonstrating a few things that aren't necessarily, discussed in any great length in the markdown of that notebook. It's very, very terse markdown, just demonstrating what's done in the cell. I really wanted the video to be the point of explanation. All right, so I'm going to open a new window. I have a primary environment, so I'm using the Anaconda distribution. So I have an Anaconda environment named primary. And if I do a real quick conda list in that environment, so a few of the libraries that we will be relying on to a high degree, scikit-learn first and foremost. So I've got currently version 1.5.1 of scikit-learn. I'm using Python 3.12. And we're also going to use polars to kind of ingest the data. I am using the polars 1.0.0 release, but the things that I'm doing with polars are going to be very, very basic. So I think even if you're on a 0 version, or I would imagine if pandas continues to evolve and maybe those versions change, a lot of these things should work. But of course, there can always be changes. All right, so I think I closed my window, so let me open up a new one. So I'll do my conda activate primary, and then we'll do Jupyter Lab. Nice. All right, so I'm going to bring that notebook over to the main screen, and I am going to go to the dark theme. Maybe just zoom it just a little bit, and I think we'll be ready to go. All right, so I need to navigate to my desktop and in that demo folder. So I'm going to be in the folder. I've got demo. There's that diabetes prediction.csv, and I'm just going to launch a Jupyter notebook. And the libraries that we are going to import, we're going to get matplotlib.pyplot, it's PLT. We'll do NumPy as NP. We'll go ahead and import polars as PL. We'll import Seaborn as SNS. And we will do from tqdm.auto import tqdm. All right, so of course, if you get errors on any of one of those imports, it means that you might not have that package installed, or you might have misspelled something. So double check that. But if you don't have it installed, of course, if you're using just Python, you would just a python.org installation, or something else. You might have to do a pip install if you're using Anaconda environments. Just make sure, or Conda environments, I should say, just make sure that you've got the packages installed in your current environment. All right, so let's go ahead and let's use polars to read our data. So I'm going to do a pl.read CSV, and that was that diabetes prediction dataset .csv, and I am going to save that in an object called data, and we are going to print the first 5 rows of that using the head. All right, so this is going to be the data that we are going to use to demonstrate this binary classification process, right? So if you think about it, we have a data set. In this case, we don't know how many rows. We'll check that very, very shortly. But we have, each one of these rows, the way to think about this is that each one of the rows is detailing certain information about individuals, right? So we have things like their gender, their age, whether or not they've been diagnosed with hypertension or heart disease. We have some information about their smoking history, right? Do we have no information? Have they never smoked? Are they a current smoker? And there might be some other values in there. We have BMI, we have an A1C level, blood glucose level, and then we have a label right here in this column called diabetes, which is going to be an indicator of whether or not that individual has diabetes. All right, so what we want to do, let's imagine that, we're some type of a healthcare provider, and we've got, a significant amount of historical data on past patients, and we have all of this information, and we also know whether or not that individual was diagnosed with diabetes. And what we want to do is come up with a model that can use all of this information, gender, age, hypertension, all of those things, to come up with a prediction of whether or not, given the values of those various attributes or features, does this person have diabetes, right? And you can imagine that this could be employed of, saying, almost think about some type of an app where, a user would go in and plug in their information. It comes back and kind of gives them a notion of the risk level or something else. But, long story short, what we want to do is come up with a model that will allow us to say, okay, well, given these various feature values, can we come up with a model that predicts with a high degree of accuracy or some other performance metric? We'll talk about that a lot throughout this video, whether or not that individual has diabetes. All right, so we've got our data. We've talked about that. And let's just look at the shape of it. So how many observations do we have? Well, we've got 100,000. All right, so one thing that, I think I've, previously mentioned here is, I suspect that this data set is simulated, right? So it's kind of interesting that it's a nice round 100,000, but regardless, it's going to be perfect for our task. All right, so the first thing that I might want to do is just kind of get a sense of, okay, well, for each one of these columns, can I just do some basic visualization to see, how they relate to this diabetes? So for this gender column, can I look at the various values in that gender column and see, how the breakdown against diabetes is? So that is going to go ahead and maybe prime my intuition regarding what I would expect to see be important predictors in this model. All right. And let's just think through this for a couple of cases, and then we'll write out a more generic plotting function. All right, so let's just say for now, we're going to create, a thing called column label, and that's going to point to one of our columns. For now, let's just pick gender. All right, and then what we could do is we can make a matplotlib object, so plt.subplots. In this case, we'll just do 1, 1, big size equals, and then let's just say maybe, 5 by 3. All right, now one thing that we should note right here at the beginning is, if we think about the data that's contained in these various columns, we would expect them to be, very different, or we might use different techniques for visualizing based on, what we expect out of those values. For example, in gender, we might expect these to be categorical, right? We see that that column is in fact a string, and we see female, male, and maybe they have like an other. But it's going to be a discrete categories, right? So we might want to see how does diabetes vary for each one of those discrete categories. On the other hand, something like BMI, right, we see that that's a float, and those are, by definition, it being a float, those are fractional floating point values. So, these aren't discrete categories, so we might want to visualize those different. In particular, we might use something like, a bar plot or maybe a confidence interval plot for the things where we have categories or categorical data. And then for the things where we have continuous data or floating point numbers, we might use something like a line plot, scatter plot, regression plot, something like that. So if we're thinking about the categorical columns, right, so I'm thinking like gender, this hypertension appears to be a binary, either 0 or 1, heart disease, smoking history is definitely categorical, and that might be it. Everything else might very well be things that are more on measured on a continuous spectrum. And so we've got kind of two categories of plots that we want to do. All right, so let's just kind of think. So this is going to be one of our categoricals. What I would probably lean towards for our categorical variables is doing something like a point plot. So that's going to give me some confidence intervals. And what we can do, so using Seaborn, I need to say, well, my data, what am I doing? I can pass it a data frame. And for the X or the horizontal axis, I want to be, well, whatever the current value of column label is. And then the thing that I want to measure on the Y or the vertical axis will be diabetes. And we'll look at this. All right, and let's give it a few optional arguments. So I'm going to do that line style argument equals none. That's going to not join those confidence intervals with a line. And then I'm going to say, well, let's put it on the current axis. And we'll do a plt.show, maybe clean up a few things. So I'm referring to diabetes as if that's a variable. That's a column name in that data set or our data frame, which is called data. So there we go. That cleans that up just a little bit. So what we can see here is that we've got that categorical variable, in this case, gender, kind of varying along that horizontal axis. And then on the vertical axis here, we've got these proportions. And since we've given it this diabetes column, which is going to be 0 or 1, what that's actually doing is it's essentially saying, okay, well, for all of the individuals that are a particular gender, say male or female, what is the proportion of cases where we see that column value taking on a 1? So this is essentially the proportion. So if we were looking at this graph, we would see that based on these confidence intervals, it looks like the male gender has a higher proportion of instances of diabetes, right? Because that confidence interval is at a higher value, and there's no overlap between those intervals between, say, that and female or male and other. All right, let's look at another one of these columns. So let's look at maybe smoking history. So if I change that column label to smoking history, we see kind of a similar thing. So if they've never smoked or there's no info, they tend to be, somewhat of a low risk. Interestingly, the former smokers seem to be the highest, right? So current smokers seem to be almost on the same risk level as, say, someone that's never or, had ever smoked. But the former smokers seem to be the highest. And we got to think about that. That could be due to something like a correlation, right? Because for someone to be a former smoker, maybe that's indicative of people that are at an older age, right? So they've had time to pick up the habit, smoke for a while and then actually quit. Whereas a current smoker could be someone young. Again, we don't know. We'll actually look into these correlations, but it could be something associated with that. All right, so that is going to be the type of plot. I think this is a good plot for our categorical data. So I'm just going to comment that out for a second. All right, and let's look at one of our continuous values. So let's look at like this HbA1c level. All right, so for our continuous values, I would say that let's use a reg plot. So I'm going to use Seaborn reg plot. Again, we need to specify our data, which is going to be data. X is going to be our column label. And then, oops, and then Y is going to be that diabetes column values. All right, so for a reg plot, it will, let's just look at what the basic reg plot will display. All right, so what it actually does on this, on your vertical axis, again, that's essentially interpreted as that, proportion with diabetes, right? And then on the horizontal axis, in this case, you've got whatever that current column is, which is going to be our HbA1c level. All right, so we can see that, okay, well, as that horizontal axis value is increasing, right, it'll plot this linear regression line, and the scatter plot is showing, values for particular individuals. So you can see for A1C values pretty much less than 5, all of those have a proportion of 0 in that diabetes column. Once we get above 5, we start to see some mixing. And then once we're above 7, pretty much everybody that has an A1C value above 7 is going to be belonging to, the proportion of, individuals with diabetes is 100%. So this seems to be a pretty strong predictor. It kind of separates the classes pretty well. There's just this mixing region, I would say pretty much between like 5.5 and maybe 6.8, something like that on the A1C. Now, if I was doing a scatter plot, I do, because, there's probably, we know we've got 100,000 records here, so we don't see that many dots. It's because some of them are overlapping. So I might pass in some parameters to Seaborn through that scatter keywords to just make those, scatter plot look a little bit better. So I'd give it maybe an edge color, and then an alpha. Let's set the alpha to 0.05. All right, again, it doesn't so much help on this one, right? Because apparently they're, even though that is like a continuous value, that A1C, they're apparently doing it in fairly tight categories, but still. Let's check another one real quick. Let's look at maybe BMI. So column label BMI. Yeah, so this one's kind of interesting. It does seem to indicate maybe a positive relationship. So as BMI, which again is varying on that horizontal axis here, is increasing, the proportion of people with diabetes, even though again it's kind of hard to tell because again we just have so much data here, even though we see these scatter plots and they kind of look like they might be overlapping. It's just we have so many data points. Let's just see if we can bring that alpha way down to maybe 0.01, see if that helps any in seeing those regions of density. So yeah, this might be a little bit more helpful because you can see like on that, at the bottom side of the vertical axis around 0, it seems like there's more density in the lower values of BMI, whereas that kind of shifts up a little bit when you look at that, the values that are 1. All right, so we've got these two types of plots. What I'm actually going to do is I am going to take my columns here. So I'm actually going to just say data.columns. All right, so I've got my columns, and since we've got, two different types, so we've either got categorical or, kind of continuous features, what I'm actually going to do is I'm just going to make a little mapper. All right, I'm going to put my column names in there. All right, and for everything that I think is categorical, so maybe gender, hypertension, let's see, heart disease, and smoking history. And I was just holding down Control to do that multi-cursor. I'm going to say for each one of those, what we want to do is generate a point plot. All right, and then for all of the other ones, excluding diabetes, what I want to do is generate a reg plot. Nice. All right, I'm going to take diabetes out of there. So I've got this plot mapper, and what I'm going to do is I'm going to use that subplot mosaic utility. I've got a playlist up on matplotlib if you want to kind of learn a little bit more about that subplot mosaic utility in matplotlib. So I'm going to make a mosaic. All right, And I'm going to have, let's say, 3 rows of subplots. All right, so in the first, I'm going to put, let me get those columns again, data.columns, so I don't just sit here and type everything. So I'm going to do gender, age, and hypertension. Gender, age, hypertension in that first row. And then I'll do heart disease, smoking history, and BMI in that second row. And then I'll do HbA1c and blood glucose in that third row. And since, you know, the other 2 rows, the first 2 rows have 3 items, I'm going to put a dot string that'll create a empty plot there. So now we're not going to need our column label anymore. And what we'll do, instead of using subplots, I'm going to use subplot mosaic. All right. And I'll just hand off my mosaic. And for now, I'll just make this a 10 by 10. All right. So what we're going to do, just to show you real quick, if I were to comment all of this out. All right, so that's going to generate this mosaic, and it hands it back as this AX object, which is a dictionary where the keys correspond to the values in that mosaic, which we made correspond to columns in our data frame. And then if I were to get any one of those keys, it returns a matplotlib axis, which is going to be handy. All right, so now what we can do, we can say, well, okay, well, since we've got the keys of the mosaic right here in this plot mapper, I'm going to say, well, let's do a for loop. So I'll say for column label. And I'm going to also get the plot type out of that dictionary in the items. All right. So we're iterating through this, getting the column label and the type of plot we want. And I'm going to say, well, if the plot type equals a point plot. All right, so if that's true, what I want to do is take that piece. All right, so we'll have data, whatever the column label is, and that. And I'm going to make sure now, since we're dealing with multiple axes, remember this AX is now a dictionary. So I'm going to tell it I want the axes for that column label. All right, and then I'll do an elif. The plot type is a reg plot. All right, and then we will do the same thing here. And we got to put that, specify that axes, or that AX parameter. So I'll say AX for whatever our column label is. All right, that should be fine. What I'm going to do is just a little bit of cleanup here. So I'm going to say for each one of these axes, so as I'm going through this for loop, I'm going to grab that axis, and I'm going to take those right and top spines and set visible to false. I'm going to change the X label to whatever is the current value of the column label. And again, that's going to be the keys of this dictionary. And what I'm going to do is I'm just going to replace underscores with a empty string, and then I'm going to set this to a title case. So I'll say, okay, well, let's do a replace any underscores with an empty string, and then I'll do a dot title on that. And then I know in advance that the smoking history one is going to kind of render somewhat poorly because they're long descriptions or long values in that column. So I'm going to do a special case for it. I'm going to say, well, if it is smoking history, what I'm going to do is take that axes, get the tick params, which axis do I want? Well, I want to do the X, and then I'm going to say a label rotation equals 30. All right. Final couple things that I'm going to do is I'm just going to, these things are going to get a little bit bunched up. So I've kind of ran through this before. So I'm just going to do a subplots adjust. Give it a little bit of spacing, both vertically and horizontally. So 0.5, and then W space equals 0.5. And then I'll do a plt.save fig. And I'm going to say this is going to be our diabetes impacts. Make that a PDF file. And do that bbox inches equals tight. Because we've kind of done that subplot adjust, that could mess up our bounding box. All right, so I'm going to give this a quick little run. Make sure I have it done. So elif plot type equals regplot. It doesn't look like I put a colon there. Let's see what my next error is. So AX, instead of pines, that should be spines. All right, it's going to take it just a minute to generate because we have a good bit of data in those when it's generating all those little scatter plots. So it'll take it just a second. All right, so we see here, for gender, again, we see that the, the risk of diabetes tends to be higher for male. We see it tends to be an increasing risk as we get older. If you have hypertension, that proportion or the prevalence of diabetes tends to be larger. Same thing with heart disease. Smoking history, former smokers tend to have, a higher risk. And again, that could be correlated with age. We'll look at correlation shortly. As your BMI increases, you tend to have a higher risk. And then as your HbA1c and your blood glucose level increases, you tend to have higher risk. So we can generate this plot to just kind of, again, build some intuition, kind of explore the data, see what the trends that are going on, get an idea of the various things that are in our data. And a nice thing is you can see over here that we have generated this PDF. That did take a little bit of time to generate that plot. Let's see if it loads here. Might not like that. It's quite a big plot. Let me show you real quick. So one thing that's causing this to load, when you save a scatter plot as a PDF, it actually saves each one of those little dots in there as kind of its own little graphic, and it takes a while to render. So you can change that to a PNG. I'll run that one more time. And while that's running, I will delete that PDF file. All right, so let's let that run. So you saw how that PDF was really kind of struggling to load, and that's one thing that I've noticed, especially when you're doing scatter plots, when you have a lot of individual points. In this case, we've got 100,000. It's taking a while, but we can write that out to a PNG, and it'll be a much faster load. Even though you technically are sacrificing some resolution, you can go in there and adjust that. But now we've got our plot. We've generated it once. It took some time. So what I like to do is maybe make like a little flag variable right here, say something like generate plot. I'll set that equal to false, and I'll put an if statement to say, well, if generate plot, and I'll nest everything underneath that. All right, so now when I run this, right, if I have to do a restart run all, I'm not going to sit there and wait 30 seconds while it generates that plot. Why? Well, we've already generated it and we've stored it. All right, so speaking of a good restarting the kernel, I like to do that periodically. So I'm going to restart, clear all my outputs, and there we go. All right, so before we start doing any type of binary classification, if we look again at our data, we do have these two categorical columns. Now, there are definitely some libraries and some classifiers that can work with categorical data, but not all of them can. So it's typically a good practice to convert these to kind of like an integer representation using a technique called one-hot encoding. And to do that, we can use polars. It makes life really simple, just to make sure that every time I run this, if I were to run things out of order, things don't get messed up. I'm actually just going to repeat that read CSV just to make sure every time that this cell runs, it's getting a fresh copy of that data. And what we have to do, so if I've got data right here, and let's say that I can't work with this string, right? So these binary classifiers, a lot of times, we're talking about a machine learning algorithm. Machine learning algorithms work on numbers, not text, right? So what we'd like to do is maybe take this gender, and we've already seen in our plot, right, that in that gender we have female, male, and other categories. What we might want to do is make a column that says, hey, well, is this individual, is the gender female? Is the gender male? Yes or no? Kind of like we have for hypertension and heart disease. All right, so how can we do that? In polars, on a polars data frame, you have a method called toDummies, and you just give it a column or a list of columns. So for example, if we gave it gender, all right, you can see that it has given us back now 3 different columns: gender female, gender male, and gender other, right? And if I were to look at data.head, right, so that first individual is female, second female, then male, and so we see the 1, 1, and then the 1 in the male column. So it's just mapping those unique values in that column out to different columns, right? And it's just using those binary integer values to indicate what was the correct value. And one thing nice about polars here is it's putting the original column name first with an underscore and then the actual value that it's mapping to. All right, well, we would also want to do that for smoking history. But before we do that, let me just, make a note that typically when you're doing this type of, transformation, and this is referred to as one-hot encoding. So I'm taking a column of categorical variables and I'm kind of breaking it out into multiple columns of binary values. So when we do this, technically, in this case, we had 3 unique values: female, male, and other. Well, technically, if you tell me, the values in 2 of those columns, I know the value in the other, right? So in this case, well, gender female in that first row, that's a 1, so I know gender male and gender other are going to be 0. Likewise, let's look at this third row here. If you told me gender female is 0 and gender other is 0, well, then it has to be true that gender male is 1. Right? So technically, a lot of times when we're doing this one-hot encoding, it's if we just generate all those combinations, those are of course going to be correlated, right? Because if you give me the value for 2 of them, I can always tell you the value for the third column. So a very common thing to do is to drop one of them. And polars gives us the option of dropping the first. So we can set drop first equals true. And now we only get, instead of getting female, male, and other, well, female occurred first, so it's just giving us back the male and the other. And again, in this first row, gender male is 0 and gender other is 0, so we know that that is corresponding to a case where the gender is female. All right, so this is what we want to do. And we want to do this for both the gender column and that smoking history. So instead of providing a single value to toDummies, we can provide a list of column values. All right, so now we got all these smoking history columns, and that is perfect. So I'm going to take that toDummies statement, put it right at the end of that read CSV. That way, when I read that column or read that cell, run that cell, if I do a data.head, there we go. So we've got this one-hot encoded data. Everything is numeric. This is perfect. All right. All right, so we're getting a little bit closer to our binary classification task. And the one thing that I like to do is I am going to specify which of my columns are the target column and which are the feature columns, or the things that we think are predictive. So the target, the thing that we're trying to learn to predict, is going to be the values in that diabetes column. And if I do features, in this case, I'm going to consider every other column a feature. And this is not always the case. I just want to make a note of that. like, we might have a column that was like, patient ID number, which is like a unique identifier for the patient. If that's the case, you do not want to include that column, right? Because we don't believe that that is predictive, right? It's going to be unique to the individual. Or we might have other information in here that has, we can't, have any reason to believe it would be affecting whether or not a person has diabetes. You might also just say, well, I don't want to bring in things like, their age or their gender, right? So you don't necessarily want to use all of your variables. And again, there could be some ethical, implications of you doing that, right? So what if you had, like this was, you were trying to predict credit risk and you were doing things like ethnicity. You don't want to do that. That would be, the model could learn behaviors that are just kind of an artifact of the way that things historically have been, not how they should be, right? So you want to be careful with that. So again, the reason I say that is I'm going to just say, right, so a function here that basically pulls in all of the columns except for the target, but that's not always what you want to do. Look at your columns, think about the ethical implications of those, think about, whether or not those columns are, had some reason that you feel could be correlated with what you're trying to predict when you're doing this. But in our case, we don't have that issue, so I'm just going to say call in data.columns if that column is not equal to my target. All right, so at the end of this, I've got a list of all of my columns except for my target. All right, and the last thing that I want to do before we start going into any type of classification is I just want to look at the correlation between these features, because one thing that can cause some of these predictive models a little bit of a headache is if you have a lot of features that move in the same direction. So as one goes up, the other goes up, right? One thing that we were talking about when we looked at that plot was like, this notion of, well, why is it that former smokers are at a higher risk than, say, current smokers, right? That seems to be a little bit counterintuitive, right? And we said, well, maybe it's correlated with age, right? So maybe it's more likely that a former smoker is older. Well, we need to check if those things are correlated. And what I'm going to do is, now that we've got our features, I'm just going to select using polars. I'm going to select my features. All right, so I'm grabbing those columns. I'm just going to make that a pandas data frame real quick, because pandas data frames have a nice core method, which I can call on that data frame, and it'll give me the correlation among all of the column variables or all the column values. So in this case, my column values corresponded to my features, so I'm getting the correlation between those. And I'm going to call this my correlation df. And then we'll generate a really simple plot using Seaborn. So I'm going to do fig ax equals plt.subplots 1 1. Fig size equals, let's do a 7 by 7. And then I would do a heat map. All right, so I'm going to give it my data is going to be, let's see, what's the argument? Yes, so data is going to be that. I like to do the color map equal to cool warm, so that higher values are red, lower values are blue. Since we're plotting correlation, I know that the minimum value that can take is 1.0, and the maximum value it can take is, or minimum value is negative 1.0, and the max is 1.0. So I'm going to go ahead and set that. Otherwise, what it will do is it will set the extent of what it plots to the minimum and maximum values, and that can, when you're looking at a heat map, especially for correlation, that can give you some. If you just look at it visually and really don't pay attention to the values, it can be misleading. I'm going to take off the color bar, and I'm going to annotate the cells, and I am going to do the annotation as a floating point with 2 decimal places, so that needs to be a string there. I like to do line widths just to make it everything kind of pop a little bit more. So I'm going to say line width is 0.1 and line color is equal to K. And then I'll do a plt.show All right, and we get this matrix right here. Let me make that just a little bit small. Let's do, it's gonna get a little bit cramped. All right, so my numbers are getting a little bit cramped now, but we can kind of visually look at this. We do see that there are some that are, have higher or greater than 0 correlations, but nothing is really excessively large. I would be looking for things that are like 0.6, 0.5 or above. Those would be highly correlated. And there's nothing that's really too big on the low side. Let's look at that one that we were concerned about. So we were saying, well, smoking history current. If we look at its kind of correlations here, so it wasn't smoking history current, it was smoking history former, right? So if we were to pull up that plot, it was that case where it was the former, they had that high value. So smoking history former, and if we look, we see a 0.22 correlation with age. So it seems that there is some positive correlation with them being a former smoker and their age, and also the BMI. So as we get older, our body mass index tends to grow up, it seems, or go up. But still, those correlations are, I would not by any stretch call those high correlations. So nothing at this point to give me enough pause that I would say, we need to remove those variables or remove one of those variables. If I did see a correlation value or a pair between two features that was really, really high, I would probably make the decision to remove one of the features, because again, if we have really, really high correlations, that can cause some issues for our model, because if two things are moving, if as one increases, the other also increases, the model might, struggle to figure out, well, which one of those two features that are correlated are actually resulting in the change in the thing that we're trying to predict, or the target variable. So we might want to help that out by removing one. All right, so we've done some plotting at this point, some just basic, data visualization, as we've seen a few times in this plot. Now we've looked into correlation, so everything looks good. So I think at this point we are ready to start doing our predictive modeling. One thing, remember, I've got the target variable stored as a variable. So this is the column name that we're trying to predict, and we do have a list of features. All right, and one thing I like to do before I start doing any type of prediction is just get that target column and look at the mean. So what this is telling me, if you recall, so our target column, these are zeros or ones, right? So if I were to get the max value out of this column, it's going to be a 1, and the min value is going to be a 0. That's why we're calling this a binary classification. So we're trying to predict a target that takes on two different values. Right, so it's a binary classification. We want to get a model to predict which of the two classes, in this case 0 or 1, each one of those rows should belong to. So if we take the mean of that column, since there are zeros and ones, that's giving us the proportion of rows that are equal to 1. All right, and we see that it's 0.085, so 8.5% of the values in that column are 1. All right, so this is always really important. So if you're doing some type of a binary classification test, this kind of at least gives you a baseline of, what you should expect out of the performance of your model. So in this case, 8.5% of the instances in that column are ones. So, I can theoretically, let's think about it this way. So what if I take 1 minus that? So 91.5% of the values in that column are zeros. So what that means is, well, I could just predict nobody has diabetes or nobody's at risk for diabetes, and I would be right 91.5% of the time, right? Now, is that a good model? Well, you might look at the accuracy. If we're just looking at the number, we're like, well, we're 91.5% accurate. Well, we can achieve that with just predicting nobody has diabetes. So we really haven't learned anything. So this baseline accuracy right here, this is kind of, we've got to beat this. If we do worse than this, we haven't really learned anything. And it's always useful to kind of recognize that. Another thing that we want to recognize about this is, okay, well, 91.5% are zeros, so that means we have an imbalance in the distribution of the thing that we're trying to predict, right? It's not 50-50. Right, so in this case, we have a lot more negative instances, so cases where diabetes is 0, than we do positive instances, okay? And we want to be careful about that. All right. All right. So the first thing that we're going to do when we do binary classification is what we want to do is take our data set and we actually want to split it into two different data sets. One called a training data set and one called a testing data set. And the reason we want to do this is because when we're training the model, right, we're going to have to give it some data and it's going to learn from the patterns in that data how it can make a prediction. Well, we don't want to just give it all the data because technically what the model can do, these are very sophisticated models and computers are fast, it can just learn the data, right? So it can just say, oh, well, I learned that each one of these rows, what their labels were, and it generates predictions. It just looks up and says, well, here's what the row labels were. So it hasn't really learned anything, but it can achieve really, really good accuracy. So what we want to do is we want to split the data set, and our training data set is what we will train the model on, and then we will use our testing data set to actually assess its ability to make correct predictions. All right. Now, we're going to be looking at scikit-learn, and scikit-learn has some amazing utilities for doing this. So I'll probably pop back and forth to the documentation. We'll definitely be looking at doc strings as we go along. But what we're going to do for this test train split or training or splitting this data set is we want to import from scikit-learn.model selection. We want to import a function called train test split. All right. And this is the typical thing for scikit-learn. We oftentimes do not just say, import scikit-learn because it's a very large library, a lot of different modules. That import could be relatively slow. So what you'll see me do is just import bits and pieces that I need as we go along. All right, so let's look at train test split. I'm going to open parenthesis and hold down Shift and Tab to pull up the doc string because scikit-learn, in my opinion, is one of the best libraries in the Python ecosystem as far as documentation. They have a lot of little code snippets that we can largely just copy and see exactly how things are going to work. All right, so let's see what it takes in. So it takes in some arrays. We can give it a test size, a train size, or I think you would just want to specify one of those. It will do this splitting randomly. So you can specify a random state. By default, it shuffles the data before it does that random split. And then importantly, we've got this stratify. So what stratification does is you will give it an array like, a vector, essentially an array. And what it will do when it does that split, it will make sure that the data in both of those splits have equal representation for whatever you have in that vector. So this is important for our case because remember, when we look at that target column, it was imbalanced, right? So 91.5% of those values are zeros. Well, what you don't want to do is split your data in a way where the training data set has, maybe it's, all the zeros got put in the training set. So when you hand that off to the model, it says, well, I'm just learning that everybody's a zero. Maybe all of your ones got split into the test set, and then so you trained it on data that was not representative of what you're going to see in the test set. So what we're going to do is we're going to say, well, we want to stratify off of that target column, and that's going to make sure that we have the exact same proportion or as close as possible in both those training and testing sets. All right, now again, I like to look at the documentation. We can do oftentimes just a little quick copy and paste. So in this case, we see it's got this snippet of code here, and I'm going to tell you what it wants. All right, so I'm going to take that little ellipsis out. All right, so this was what the documentation had. So x, y, test size equals 0.33, and then a random state of 42. What this x is that needs to be your feature data. So in our case, we have data, and we want to give it our features. All right. And then y is supposed to be the data for your target. So I'm going to say, well, get my data and just grab the target column. All right, so I'm going to break this out over a couple of rows. All right, what I am going to do is I am going to do a test size of 20%. So that's going to say, well, take the data and split it such that 20% of the instances are in my testing set, and then the remainder are going to be in my training set, so 80%. All right, so if we run this, it gives us back 4 objects. So if we look at xtrain, all right, so this is a data set of our features. So if I were to go all the way out here, we do not have our diabetes column, the thing we're trying to predict. All right, and notice that it's 80,000 rows. Well, why is that? Well, we said we wanted 20% of our data, which we originally had 100,000, to go in our testing set. So now if I look at xtest, there's the other 20,000 that we're going to do our evaluation on. All right, so it gives us training, xtrain, and then it also gives us xtest, and then it also gives us ytrain, which is just going to be that vector of that diabetes column. And when scikit-learn's doing this splitting up, it's making sure that, okay, well, this 0, that first value in this ytrain corresponds to the features in the first row of xtrain. And then we also have ytest. All right. All right, now just notice right now, so ytest, if I were to do the mean, right, so in this case, it actually did a pretty good split, right? So about, 8.5% of the instances in ytest are positive. And then if I were to do the train, right, it's a little bit lower, right? So we did have imbalanced data, but it did okay, right? So they're pretty close to one another, so this wouldn't be too concerning. But sometimes you have class imbalances that are extremely severe, like you might only have, less than 1% be positive classes. Like if you're trying to do, loan defaults or something like that, those positive cases are very rare. So what if we want to make sure that those are as close as possible? Well, I can do stratify. And I can just stratify, just say, hey, we'll use the values in that target column to do the stratification. Now when I run that, we got 0.85 or 0.085 and 0.085. So it makes sure that they are as balanced as it can be. I'm going to do a real quick restart run all. Let's pop down. All right, so now we've got our training and testing data. So up to this point, we've just done some basic exploratory analysis. This handles doing that splitting. So we've got xtrain and xtest for our features, ytrain and ytest for the things that we're trying to predict or our target. So now we're ready to actually run a classifier. All right, so we're going to start really, really simple. And we are going to, and let me just see if I can pull this up really quick. Let me do an incognito window. And I'm going to say supervised learning scikit-learn. All right, so if you put in that string, supervised learning scikit-learn, you'll be taken to the documentation where they have a list of models, right? And some of these are for regression tasks, some are for classification tasks, but they have a tremendous amount of models, right? And they have a very good documentation, right? Well, we're going to start with it is a decision tree model, in particular a decision tree for classification. So I just put in that supervised learning. It took me to that documentation page, and I'm going to get a decision tree for classification, right? It talks about, how to do that. And here's that decision tree classifier. We can go to the docs for it. And again, the nice thing about scikit-learn, their documentation is very good, right? So they show you right here, hey, well, you need to import this thing. You need to, do some type of a CLF equals decision tree classifier. Let's see if they got some additional examples at the bottom here. Usually I'm going to see how far. Let's see, I think I might have passed it. I know I'm hurting eyes right now. Let's see, so was that the only example that they gave? Okay, so in this case, they're just doing, from scikit-learn, and then they make a decision tree classifier. And in this case, they're not showing you calling the .fit. They're doing like a cross-validation score. But we'll see this. Let's just copy this piece. So from sklearn tree.import decision tree classifier. That's going to be how we bring in that module or that estimator. And then I'm also going to do sklearn.tree import export text. So we can actually visualize what it's learning. So that imports that decision tree classifier. And if we were to go back to that documentation, we can say, well, then we've got to instantiate a version of that. So CLF equals decision tree classifier. All right, so I'm going to do that right here. What they didn't show is once you've instantiated a version of that classifier, then you will need to do a clf.fit. All right, and then you will give it your training feature data and then your training target data. Done. Classifier is fit. All right, so now I've got this decision tree classifier. You can kind of get some information, so that thing is fitted. You can get documentation. They've done a real nice job of making that really available. I did set a random seed, so we're going to look a little bit more at the parameters of a decision tree classifier shortly, but one of them is a random state. So some of these algorithms, these classifiers, do have a random component, so if you want them to be repeatable, you can set that random state. All right, so now we've got this CLF, this fitted classifier, decision tree classifier. And what you can do if you want to see its performance, well, let's do it on our training data set. All right, so if I give it some X and Y, it's going to report the mean accuracy. All right, now accuracy might not be the best thing, but let's just see how it does. So I'm going to give it my training feature data and then my training target data. All right, so accuracy is saying it's about 99.92% accurate. And then if we were to do this on our testing data, X test and Y test, all right, so about 95.2. So a few things that I want to take us to pause and take in at this point. All right, so first off, remember our baseline accuracy. So if I predicted nobody was at risk for diabetes or had diabetes, I could be 91.5% accurate, right, with that very naive classification. Well, in this case, it seems like on the training data, we were like 99.9% accurate. But on the testing data, we were less accurate than we were on the data that we trained with. And you might say, well, gosh, well, that makes sense, right? Because we haven't seen it before. But we still do get some predictive lift. And what do I mean by that? Well, we're right 95.2% of the time. So if we were to just guess nobody had diabetes, they were all zeros, we'd be right 91.5. And so we're 95.22. So, we did get some improvement, right? So it seems like something was learned. Let's see exactly what it learned. All right, what I can do, so remember I imported that export text. This works with decision trees, and what you have to do is give it the decision tree model, and you can give it your feature names. So I'm going to say, well, my decision tree model, we call that CLF, and my feature names, well, we've got that stored way up here in a variable called features. All right. So what this is going to do, I'm going to say this is going to be my DT string. All right. And if you were to print that, or just to use Jupyter, put it at the last line, it looks really, really ugly, right? But notice there's some \n's in there. There's a lot. And if we print this, it actually shows us how a decision tree classifier is working. All right, so one thing that I'm not going to do in this video is kind of go into the details of each classifier. I'm going to have additional playlists up that are looking at machine learning, artificial intelligence techniques, and I might give those a little bit deeper treatment there. But I'm really just focused on, here showing you how to implement binary classification in scikit-learn. So not going into too much detail, but basically what a decision tree does is it looks at your feature space and it's saying, okay, well, given the relationship between this feature's values and the thing that I'm trying to predict, if I were to make a cut right here and say anything above this is one split in a tree, how can we parse up this space to get different class level labels? So for example, if your A1C is less than 6.7 and your blood glucose is less than 210 and your age is less than 53.5 and your BMI is less than 38.2 and your hypertension is less than 0.5 and your A1C is less than 5.35, I'm going to label you a 0. All right, so it's just basically, you can almost think of it as like a flow chart of navigating this feature space until it gets down to a prediction, right? And again, that's kind of where we, built our intuition earlier. So think about that last split, or the second to last, well, or a third to last, I'm sorry. I'm getting lost in this deep tree. It is this one right here. So A1C is less than 5.35. They're saying it's a 0. Well, we can kind of look back at our image and look at our A1C, and yeah, when it's less than 5.35 in that, kind of region, again, the HbA1c is at the bottom left of that subplot. Well, yeah, when it was lower than 5.35, pretty much everybody was a 0. So that's kind of how it's doing. All right, well, here's the thing to realize. Notice that this is a very extensive tree. It goes on for a very long time, okay? And some of these branches are truncated, right? Saying, well, I'm not going to show anything there. So, it's a very deep tree. And one thing that it's actually doing, if you notice, like on our we did really well on that training set, but then we didn't do as well on the test set. Well, that's an indicator that what this model is actually doing is it's overfitting the problem. So the structure that it's learned is way too specific, right? It learned a very specific structure based on what it saw in the training data, but then when we apply that same structure to the test, our performance declines. So whenever you're seeing these gaps between your training and your testing scores, that's usually an indicator that you've done, to some degree, you've overfit the data. Because, yeah, it does really well in your training data, but it's not generalizing very well to your test data. All right, well, how can we get around that? I'm going to comment out that long string, and I'm going to copy that decision tree classifier code right back down here. All right. So let's look at this. And what we've got is, let's see, actually one thing before I start showing you how to get around that, I want to show you one additional little plotting thing that you can do. So right now I haven't done anything with that classifier. So we were just looking at, in this case, we're looking at, okay, when we're doing those scores, that's the mean accuracy. So again, on the training set, it's about 99.9 and then 95.2 on the test set. Well, you got to think about it. Sometimes accuracy might not be the best metric. All right, so let's look at this. All right, so first off, what I'm going to do is I'm going to import from scikit-learn.metrics. I'm going to import something called confusion, so capital C. It's a confusion matrix display. All right, and if I do a dot on that, it's got two options. So from predictions and from estimator. Well, we've got an estimator fit. What we need to do is give it an estimator and then X and Y, and it can generate a confusion matrix. Well, what is a confusion matrix? Well, let's see. So I'm going to give it my fit CLF, and I'm going to actually give it my test data. So I'm going to say, well, what are the parameters? I think it was X equals X test, and then we'll say Y equals Y test. I think that was the parameters, yeah. X, capital X and lowercase y. And I'm going to put a semicolon at the end. That's just going to hide some nonsense that it plots along with this. All right, so what this confusion matrix does is it's showing you not only what was your accuracy, but how did you miss? All right, so on the left hand or on that vertical axis, it's saying, okay, well, what was the true label or the true value of the target for each instance? And then along the horizontal, it's saying, well, what was the predicted? So if we look in one of those cells, it's saying, well, okay, well, you had a particular true label and a particular predicted label. Well, what was the number of instances that fall into that combination? So for example, in the upper left cell, all right, we see that's where true label is 0. So the person, that row, did not have diabetes. And then we predicted they didn't have diabetes. All right, so that's a true negative, right? They did not have diabetes, and we predicted that correctly. If we look in the bottom right, these are instances where the individuals truly did have diabetes, and we predicted that they had diabetes. Okay, so those are your true positives. If we look in the upper right, okay, they did not have diabetes, so the true label is 0, but we predicted that they did. All right, so that's a false positive, right? We gave a false positive prediction, And then the bottom left is likewise going to be a false negative. All right, so they truly have diabetes or at high risk for diabetes, and we predicted they don't. All right. Now, when we're just doing this score, right, so this CLF.score, it's just saying, well, overall, how accurate were you, right? So for the times that they were true, how many times you predict they were true, and for the times that they were negative, how many times you predict they were negative. But if you think about it, the consequences of these errors are going to be different, right? So in particular, if I would say it's much more severe to make a bad prediction in the sense where an individual actually is at high risk for diabetes, but we predict 0, because that could lead to a case of us just saying, well, no, you're good, right? You're fine. Don't worry about it. Do as you've been doing, right? So those false negatives, where that individual is at high risk, but we predict that they are not, those are much more dire than, say, a false positive of me saying, well, given your markers, you might be at a higher risk of diabetes. So go ahead and do these interventions. So, you might be able to do some type of preventive measure, which even if they, maybe they aren't really at high risk or have diabetes, but I think that's going to be less harm to the individual than us saying, well, you know what, you don't really have any of the indicators of diabetes when in fact they do, right? So we need to think about that. We'll see how to address that to a degree as best we can later on. All right, so this is, accuracy gives us a measure of just, how, what's the proportion of time we're correct, whereas we can actually use these confusion matrices to kind of look and say, well, where did we miss, and start thinking about the consequences of those errors. All right, well, we saw that this model did not generalize very well, right? I mean, we did get some predictive lift, but our training performance is better than our testing performance. And we saw that classifier that it fit, that decision tree, that flowchart logic was quite involved. So we can kind of see the overfitting. Well, how can we affect that? Well, you can affect it with hyperparameters. So each one of the classifiers, each one of these estimators in scikit-learn, these are algorithms, right? So they're going to have parameters that you can set that control those algorithms. All right, and we're just going to, here's a decision tree classifier. I'm just inside the parentheses, shift tab, and we can see the various parameters that are available, like max depth, class weight, the max features. Right? And just to show you really quickly what the effect of that would be, let's just look at this max depth. So by default, it's set to none. Right? And if we look at max depth, it says, okay, well, this controls the maximum depth of the tree. If none, it continues to expand until all leaves are pure. So basically, it's just saying it will just continue to grow that tree as deep as it needs to until at the end of each one of those splits, it's only, all the instances there are zeros or ones. Again, not going into a lot of details on the algorithms, but this is kind of a key contributor to that overfitting. All right, to see that, I'm going to change this. I'm going to say, well, let's fit a new decision tree where max depth is equal to 3. I'll keep that random state at 0. I'll do a CLF fit on that. And then I'm going to copy down my scores. So put all this together. So my score for my test, score for train, and then I'm going to get my confusion matrix on my test. I'm going to put all that together. All right, I'm going to say, well, I want to print statement around those, and we'll just do an F string equals. All right, and yeah, it should be fine. And then instead of doing all that again, it might be easier just to change this to test. All right, so what we're going to do, we're going to fit a new classifier, a new decision tree on our training set. We're limiting that max depth to 3. And then we're going to print the score. Again, that's just going to be the accuracy on our training and testing sets. And then we'll plot a confusion matrix with that newly fit classifier. All right, so let's look at this. So first off, notice that we lost some accuracy on our training set. So 97.17, whereas before we were like 99.9. However, notice that our testing performance is much better, and it's pretty close to our training. So this model, even though that when we fit it, it had never seen the testing data set, the patterns that it learned are now able to generalize a little bit better, right? And if we look at the errors that we make, right? So we actually make no errors where it's true label is 0 and we predict 1. So we make, no false positives. We do make a good bit of false negatives though, right? So maybe we can improve that, maybe we can't, right? But ultimately it seems to generalize a little bit better, and that is because of our hyperparameters. And what I'm going to do is I'm going to copy that decision tree string down below, right? So let's print that for our newly fit decision tree. And we see it's a much simpler structure, right? So it's basically A1C and blood glucose. Even though age does get in there, notice that the only time that it's included in a split is right here, and both times the class is 0. So it's looking like, A1C and blood glucose. So if your A1C is less than 6.7, but your blood glucose is greater than 210, it's going to classify you as a 1. Or if your your A1C is greater than 6.7, you're going to get classified as a 1. All right, so a much simpler structure. And this is actually, really nice. Decision trees are not the most powerful algorithm, but I love the interpretability because you can just print this out and you can understand exactly why it's making those predictions. All right, so a lot of times people talk about machine learning being a black box. In this case, it's not a black box, right? We see exactly what that logic is going into making those decisions, right? All right, so at this point, we see that hyperparameters can really change the performance of our algorithms. But what do we want to do, right? So if we go back up to this decision tree and I look, well, there's a lot of different parameters. Do we want to do each one of these individually and keep note of which one performed best? And it could be that it's just the way that we split our training and testing set. So maybe if we did a different split, remember we can change that with that random state when we did the train test split. Maybe if we did a different split, maybe it would do just, really poor. Maybe we just got, a particular example that ended up showing us this result. So how do we want to do that experimentation? All right, that's where the next utility that I'm going to look at comes in. And what we'll do is from scikit-learn.model selection, we're going to import a utility called grid search CV. All right, and what it allows you to do is actually do a search on the hyperparameters in a essentially a very controlled manner, and it will consider multiple splits of your training data so that when it's coming up with an estimate of the quality of a model, it will actually do that, in a way where it's considered multiple possible ways of splitting that data up. All right, well, how does it work? Well, we'll keep on our decision tree. So I'm going to make a thing now called a base CLF. That's going to be an instance of our decision tree classifier, and I'll just set the random state equal to, say, like a 42. All right, let's look at these parameters. All right, so we've got things like max depth, and then we've got criterion. So max depth, we saw we can set that chain that's essentially limits how deep our tree will go. And then let's look at criterion. That could be Gini, entropy, or log loss. Well, let's say we wanted to test Gini and entropy. All right, what you have to do is you will want to set up a dictionary. In this case, I'm going to call it param grid, where the keys correspond to hyperparameters. So like max depth could be a key. All right, and you can provide a list of possible values. So we could say 2, 3, and 4. So we want to try max depth of 2, 3, or 4. And then what's another parameter? We said we would do criterion was going to be Gini or entropy. All right, now of course you could put more hyperparameters, and what this is going to do is it's going to run all combinations. So it'll run with max depth equal 2 and Gini, max depth equal 2 and entropy, and so forth. So in this case we have 3 options of max depth and 2 options of criteria, so it's going to look at 6 possible combinations. All right, and then what you'll do, I'm going to make a variable called grid. That's going to be an instance of grid search CV. You give it your estimator. So our estimator is going to be that base CLF. All right, then you need to give it a parameter grid. In this case, I'll give it my param grid. Nice. And then you call .fit on it just like you would a regular classifier. So I'm going to give it my X train and my Y train. Let's look at some other arguments in here. All right, so notice this CV. So remember I told you it's going to look across multiple different splits. That CV parameter actually controls that. So CV, those are called cross-validation splits. If it's none, it's going to use what's called five-fold cross-validation. And basically what it's going to do is it's going to take that training data and it's going to break it into 5 different chunks. And the first time it runs through, it's going to run through and compute the performance of those parameter grids, where it uses the first 4 of those 5 chunks as the training data, and it compares it against the last chunk. And then in the next run, it'll use the first, 3rd, 4th, and 5th chunks to train and compare the performance against the second, and so forth. If you set the cross-validation to 10, right, it'll do that with 10 different splits, so you'll run more variations. Right, and it's going to compute the average performance across all of those. All right, so we could do a fit, and then just to show you real quick, I'll just run that real quick. All right, so at the very end of this, it says, hey, you know, this best estimator is a decision tree, and I found max depth equal to 2. It's actually not giving me the value for criterion, which if it's the default, it usually doesn't. So that must mean that the best one had Gini. So how can I see that? Well, if I do grid and hit tab, it's got this best params. So it said, yep, max depth of 2 and a Gini criterion was best. And the nice thing is, by default, when you're running this, run a grid search, it has this refit equals true. So at the very end, it will refit the best model, and you can get that out with best estimator. So that is the one that performed best. So at the very end of this, I can say, well, this is going to be my best CLF. It's going to be that. And then we can copy all of our code from above. So I'm going to get the scoring and the confusion matrix. All right, I got to change this instead of CLF to best CLF. All right, so this is what we were able to get out of that. All right, so let me cut that. All right, so let's see, previously when we did, we got 9723, so it looks like we found roughly the same thing, right? So we weren't able to improve that, right? But that's how you can automate that search. I do want to show you just a few additional things. So one thing that you can do, and I'm going to go ahead and do this, and again, without a whole lot of explanation. So this notion, you know, grid search, I'm saying, is looking at all of those combinations and it's finding the best one, right? Well, best by what measure, right? We've already talked about, well, we might want to give preference to, you know, minimizing, you know, false negatives or something like that. You can affect that with this scoring. All right, so if we look up, let's just look up the documentation real quick for grid search CV. All right, so if I go to that documentation, we got that scoring metric. And if you go here, it says, hey, well, scoring can be a you know, represents a single score. It can be a string. All right, so it gives you a link here where you can go see possible strings, right? So you can say, well, it's accuracy or balanced accuracy or any one of these things, like F1 is very popular, or recall. And so you can actually change, while grid search, when it's doing that evaluation, what do you want to be, you know, the metric used to determine which model is best. And some of these metrics will, you know, prefer just overall accuracy, or some will kind of, you know, look at, you know, making sure that you do the best predictions on positive instances. So a lot of different metrics right here. Of course, we're not going to go through all of them. And these are metrics for classification. It's got metrics for clustering. It's got some metrics for regression. So a lot of flexibility. So I'm going to use a recall metric just to show you how you can change that. And I think recall is an appropriate metric for this problem. So it's looking at the proportion of times that you correctly score positive instances. All right, so we can change scoring is equal to recall. and we can run that. But again, it's not going to change this estimator a whole lot. All right, so 97.23, we will see a change towards the end with a different classifier. All right, so that runs, it does that search. If we wanted to search other parameters, we can of course make sure that they map to hyperparameters, and then we can provide it with acceptable values. All right, I'm going to do it real quick. I'm going to restart clear all outputs. Go down, fit. All right, great. That time we got a warning. Wouldn't worry about that too much. Let's see. I think I've got something out. Let's look at this real quick. So I've got base CLF, and then I've got that grid, and then I've seen that estimator param grid scoring is equal to that grid best estimator. That looks fine. 9723 right there. Okay. My eyes were playing tricks on me. All right. So what if we wanted to do a more sophisticated model, right? So decision trees are very interpretable, but they are perhaps not the most powerful models. So what we're going to do is I want to show you at this point just how easy it is. Again, this kind of is me kind of bragging on scikit-learn developers and their vision for this API. They've made it very, very nice for kind of interchanging and trying different models. So for example, let's go back to the docs. I'm just going to do that search query again. I'm going to say supervised learning scikit-learn. All right. So instead of doing just a simple decision tree, what if we wanted to do an ensemble like a random forest? All right. So the documentation kind of takes us there. We've got a random forest classifier, and as you can maybe be thinking of in the name, a random forest is multiple decision trees. So what it does is it fits multiple decision trees using different combinations of feature columns and rows of the data set, and it essentially fits a bunch of them, and they each make a prediction, and it uses the majority prediction as the prediction. So for a particular instance, right, let's say we got a random forest that has 100 decision trees or 100 estimators. Each one of those 100 estimators will make a prediction for that instance, and then the majority, if say 60% of them predict it's a 1, that's the prediction it's going to go with. All right, so if we go down to the bottom, we can see the documentation. So we want to use from scikit-learn ensemble to get that classifier. So I'm just going to copy that there, go back to my code, and here was our original decision tree. All we need to do is, first off, right in front of that is where I need to import that new estimator. So I want to say, okay, from that import random forest, and then for my base classifier, I'm just going to say it's going to be a random forest, and there's a random state. Let me actually import this right above so I can get my tab completion working. All right. So now if we look at the parameters, right, it has a random state. So I'm just going to set that equal to 42. And let's go ahead and do grid search. So what are my hyperparameters? Well, we got a max depth, we got criterion again, because again, it is fitting decision trees. And then let's add this in estimator. So this is the number of decision trees that it will fit. So I'm going to make a new parameter, say we want to experiment on in estimators, and let's maybe do 25, 50, and 100. All right. And then everything else works, right? So I just changed that base classifier out. I've updated that parameter grid, and we're good. Now I do want to show you another issue that scikit-learn has made very convenient for you to overcome. So what I'm showing right now is my process monitor of my computer. So in the top graph, that's my CPU. So I've got essentially like 16 threads that can be running. So it's an 8-core machine. And then the bottom is my memory. Now watch what happens when I run this. Right, so remember, I'm going to be running all these combinations for in estimators, max depth, and criterion, and it's a random forest. So when in estimators is 25, I'm actually fitting 25 decision trees. just for that. Or if it's 100, I'm fitting 100. So it's a lot more computationally intensive. All right, so I'm going to run this, still running. And if we look, right, look at that top plot on my resource monitor. I've got all of these cores and it's not using them, right? Even though it's fitting a lot of different independent classifiers, all these combinations, it's taking quite some time, right? It's still running here, and it's not really utilizing my CPU. So I'm going to show you another important parameter. I'm going to stop that computation. All right, so it wasn't complete yet. When you do grid search, since it's doing all of these combinations, technically it can run those in parallel on different cores. So for example, it could do the case where n estimators is 25, max depth is 2, and criterion is Gini on one core, and then on another core do the combination where n estimators is 25, max depth is 3, and criterion is Gini on a different core, because those things are independent. All right, to tell scikit-learn you want to do that, when you do the grid search, you see that n-jobs parameter is by default set to none. If we look at that, all right, so n-jobs, when that's none, it means you're going to do 1. If you set it to -1, right, it means you can use all processors, and this is specifying the number of jobs to run in parallel. So let's do that. Let's say n-jobs equals -1. All right, so this is what my resource monitor looks like. I'm going to kick that off, and now we pull it up, and now you can see we got a much better utilization of our machine. All right, so pretty much in this case I gave it -1, so it's going to be using all of my cores. All right, that finished. Great. All right, and again it has found essentially we were still not able to beat that original model. However, that ran much quicker. We got a much better utilization out of our machine. All right, let's try one additional classifier. All right, so up to this point, right, we've looked at and we've seen with random forest, right, it didn't necessarily improve. It's a bunch of different decision trees. We're still in a case right now where we've got like 554 false negatives. We'd love to get that number down if we could. So far we haven't been able to do that. Let's look at one additional classifier, just again to show you a little bit how easy this is. So I'm going to go back. So here we are at that supervised learning. We were at ensembles. Let's see if we've got, let's look at this gradient boosted trees. So they've got a newer one. So in scikit-learn 021, they've got this gradient boosted tree. And again, I'm not going to go into detail. You can say it's a tree model, so it is inspired again. It has some relationship to decision trees, but it's a hist gradient boosting classifier. So gradient boosting classifiers are very popular. You know, XGBoost is a boosting classifier, and it's implemented in a separate library, but it's extremely, they recognized how the popularity of scikit-learn, and they developed it where it's plug and play, and it's pretty much, if you're doing binary classification like we're doing here on like tabular data, I mean it's phenomenal. I think it would be, you know, it oftentimes is the winning algorithm in competitions related to binary classification. So this one's kind of related to that. Let's just open that up in a new tab. So his gradient boosting classifier. So if I scroll down in my documentation to my example, all right, so all I need to do, I've got to do this import. So let's go back to our code real quick. I'm going to copy that piece. All right, so I'm going to import his gradient boosting, copy my random forest code. All right, and now instead of being a random forest, I'm going to do a his gradient boosting classifier. We'll keep that random state at 42. Notice our parameters have changed fairly significantly, right? We've got max depth again, but we don't have criterion anymore, so we can't put that in that parameter grid. I don't think we have it. I don't see it, right? And we have things like learning rate. We don't have n estimators anymore, I don't believe. Let's see, does it have n estimators? No, has a learning rate. So let's just put this learning rate in here. Let's see if we can understand how that's changing. And let's do max depth equal, let's allow 1 as well. Because sometimes these boosting classifiers, they need really weak learners. So they're essentially a sophisticated, and this is not correct, explicitly, but the way to think about it is they're kind of a sophisticated random forest, even though the way that boosting is working is quite a bit different than the way a random forest. So a random forest is fitting a collection and giving each one of those decision trees a vote. Whereas boosting, they're essentially kind of doing it in sequence. They're fitting a simple decision tree, they're looking where it makes mistakes, and then they're attempting to leverage those errors and improve upon them. So it's quite different, but it's still, they're fitting a lot of decision trees or a lot of weak learners. So we got a learning rate, and I think by default that was 0.1. So let's say 0.05, 0.1, and then let's do a 0.2. Just to understand how that's working. All right, so there's my classifier, there's my parameter grid. I'm going to say recall again. Let's change that in jobs. I was thinking I am recording this, so I don't want to just kill my processors. It might mess up the recording. Hopefully it hasn't already. So I'm going to say in jobs is equal to 10, and there we go. Let's let that run. Let's look at our resources. So yeah, I'm leaving a little bit of capacity on there for me. That was quick. Yeah, and let's take a look at this. So my best score, which again, this is accuracy, 97245. So 9723. So it is a little bit more accurate, actually, than the random forest. But the other thing is, notice right here, our false negatives is 529 versus 554. So we've reduced the false negatives. So if we remember talking about, there's kind of asymmetric risk, right? So if I tell somebody they don't have diabetes or are not at risk when they in fact are, that's potentially more risky than me saying, well, you are, when in fact they're not, right? And just to show you again, I use this scoring is equal to recall. Well, what if we change that scoring metric? Right, so recall, I think, should be aligned with minimizing those false negatives where we're telling them they're not. So now if we were to run this without this, it's going to be prioritizing accuracy. And we can see that changes, right? That number goes up. So that scoring does have an effect, right? And we can see we achieve the best accuracy I think we've seen. But again, we go to that recall. All right, so up to this point, what we've done is we've looked at a lot of different variations of, how do we bring in different classifiers. We've seen how easy that is with scikit-learn. We've looked at using grid search to do hyperparameter tuning for these various models in an efficient way. And we've seen that we can use that in jobs to run that in parallel, right? So we see those spikes so we can really utilize our machine. The last thing that I want to do is to kind of talk about, again, so I want to focus on the asymmetric risk that we have here. So again, we're talking about diabetes. So if a person truly has diabetes or is at risk, and we say that they're not, they don't, that's a really poor outcome for the patient, right? So we might be willing to give up even more accuracy or have a higher risk of telling someone that they are at risk of diabetes when in fact they're not, than we would vice versa. But it seems like no matter how hard we've kind of tried, we've done what we can. We've specified recall. We're doing this cross-validation. We still end up with 529. Well, what if we want to get that number down, lower, possibly at risk of, misclassifying the other way around, where we're telling people that aren't at risk of diabetes that they are likely to have it. All right, and to see this, what we got to see, so right now I've got this best CLF. That was the His gradient boosting classifier. And it has a method on it called predict. All right, so if I give it my X test data, my features, it gives me back predictions of 0s and 1s, right? So if I figure out what the max value of that is, it's a 1. So somebody somewhere in that data set has predicted somebody has diabetes. All right, and it's giving me back one prediction for each one. It's giving me back as a NumPy array. Instead of getting the predictions, the class labels, you can also get back the probabilities. All right, now if we look at this, all right, so we got 20,000 entries, which is the same number of rows that we have in our test data set, but we have two essentially values in that axis one, because this is a NumPy array, right? So you got 20,000 entries, and each one of those is a NumPy array with two values. And what these two values are the probabilities. So like this row that I've got highlighted here, the first entry in that single NumPy array there is the probability that it's a 0, and the second value is a probability it's a 1. So instead of just labeling people as 0 or 1, we can actually get the probabilities back. So for example, if I want to get the probability that each one of these individuals is a 1 or has diabetes or is at high risk of diabetes, I can say, well, give me back that NumPy array, give me all rows, but just give me that second index value in that axis 1, or that second position in the array. All right, so these are going to be, if I look at the shape of this, I've got 20,000 entries, and these are the probabilities that these people belong to that class 1, so they're at high risk of diabetes. All right, now, so this is how I can get those back. So these are going to be my positive probabilities. All right. Now, one thing I want to show you is let's see what scikit-learn is doing by default, because, okay, well, apparently it's come back with some predictions. It's got a predicted label of 0 or 1. Well, what probability did it use? Well, you can probably reasonably guess, right? So probabilities are going to range from 0 to 1, and it uses a threshold of 0.5. All right, let's see that. I'm going to import one last little thing from scikit-learn metrics. I'm going to import, instead of capital C, lower CO, and you can get the confusion matrix. So notice this is lowercase. Earlier we were using confusion matrix display, which is capital C, capital M, and capital D. Excuse me. All right, so what we can do with this, so we've got these positive probabilities. I'm going to set a threshold. Let's say 0.5. And what I'm going to do is I'm going to get back all the cases where those probabilities are greater than or equal to whatever my threshold is. All right, so that's going to be a Boolean array. I'm going to say that these are going to be my predictions. I can actually do, let's say I can wrap that. All right. And then I can make that, I think I can do an as type int to make those zeros and ones. And I'm going to say, well, these are going to be my predictions based off of that threshold value. And this confusion matrix method or function that we just brought in, you give it some true values, and then you give it some predictions, and it will report basically the same things that would go into a confusion matrix, just as an array. So for example, if I know my true, so this is based off of my test data, so X test. So if I give it Y test, that's my known values, and I give it my predictions, right, it generates this matrix. So notice we got 18 to 78 right there in that array. Well, that's exactly what we have right there in that confusion matrix plot. 22 in the upper right, 22, 1171, right? So basically when you call that confusion matrix display, it's just calling this function underneath. And we could see that when we set that threshold of 0.5 on those probabilities, we get exactly the same matrix. All right, now I can flatten this, all right, to get an array. And then I can store the first value will be my true negatives. Next will be my false positives, then my false negatives, and then my true positives. It's giving me back 4 values. So now I can say, well, I want to print. Let's go ahead and print our false positives. And let's do that. And then we'll go ahead and do our false negatives. So this is where we're missing. And again, those false negatives are perhaps more dire. All right, so in this case, we got 202 false positives, so upper right, and then 529 false negatives, lower left. All right, so if I change that threshold, right, so remember, this is the probability so when we run that classifier, it gives us a probability that that instance is a 1, right? So we're saying, well, that's got to be greater than 50% for me to classify. Well, right now, we've got a lot of false negatives, right? So these people should be a 1, but we're not predicting them as that, right? And that's probably because if that threshold's so high, they're just not quite getting there. So even though they have some risk markers, maybe, they're not crossing that threshold, so we're classing them as a 0. So if we wanted to reduce the number of false negatives, we could lower that threshold. But that's probably going to be at the expense of getting more false positives. So right now we only have 22 false positives. So let's see if we bring that threshold down to 0.25. Right, so we reduce our false negatives. Right, so we're essentially, telling more people that actually have a high risk of diabetes or already have that hey, you need to be concerned. But we're also telling a significant amount more people that don't have those risk markers that they need to be concerned about this, which again, I think that might be an appropriate trade-off, right? Because a lot of the things that are, can help kind of delay the onset of diabetes are things that are just good for general health anyway. So the risk indicators of that are perhaps a little bit lower. Again, if there's medication involved, physicians wouldn't know what that trade-off is. But just to show you here that you can affect that with that threshold, right? So this is the last kind of control mechanism that you have in place, right? Now we can see, like in this case, if I set it to, let's do 0.1, right? Yeah, we get, not as a significant reduction in false negatives, but a significant increase in false positives. All right, so let's just run a real quick little experiment. So I'm basically going to generate some thresholds. And we'll do an np.arange 0.01, I'll do 1.00. And I'm going to make some experiment data. That'll be a list. And I'll say for threshold in my thresholds here. We'll go ahead and wrap that in TQDM. All right, then I'm going to do my predictions, get my matrix there. So I'll go ahead and generate my predictions. So where positive probabilities is greater than that threshold. And again, we got those positive probabilities from our best fit classifier, binary classifier. All right, so I'm going to get my true positives and true negatives. And what I'll do, I'm going to create 2 entries in my experiment data. So I'll say experiment data.append, open close dictionary there. And I'm going to say, what's the value of the threshold? And so I'm going to take the threshold value and round that to 2. I'm going to say error type. Let's say the false positive right there. And then I'll put the count. And I'll put my FP number right there. And I'm going to do the same thing for false negatives. And then FN. All right. At the very end of this, I'm just going to convert that to a polars data frame equals pl.data frame experiment data. All right, so that runs really, really quick. If I look at this data frame that gets created, basically what I've got for each threshold, I'm looking at 2 different types of errors and counting. So when we set it to 0.01, we get 4,894 false positives and 9 false negatives. So we don't do a whole lot of false negatives, but basically, if they've got any probability that they're a 1, so any risk at all, we're basically, saying, hey, we predict that you have a 1, right? That you're at risk. All right, let's plot that real quick, and then that will be the end because it's really hard to look at it in this table of 198 values. So I'm just going to say we'll do a fig AX equals PLT dot subplots 1 1 big size equals, let's do a 6 4. I'm going to do a SNS.line plot data equals, that's called experiment data. On the X, I'm going to put that threshold value. On the Y, I'm going to put the count. And I'm going to use a hue for the error type. All right, and I'm going to go ahead and do an AX.AX, let's say a V line. I think that'll be the right one, 0.5. Right. All right, so this is showing as we change that threshold, how did the count or the number of false positives and false negatives vary? So you can kind of see, and that vertical line at 0.5, that's the default threshold that scikit-learn will use, right? But you can kind of look at this and you can see where those trade-offs lie, right? So if we look to the left, kind of at that crossover point where we're just as likely to have maybe a false negative as a false positive, that happens somewhere much lower, right? So maybe that's where you want to set that, right? I do know that we'll be at a much higher rate for false positives than false, than we currently are. But again, just looking at those asymmetric risks, ultimately, it depends on the problem, right? So again, you need to look at not just accuracy, but think about, okay, well, when we do make errors, what are the consequences? In this case, we're talking about, the health of individuals, right? And recommendations potentially for them to, do preventative care for a particular very bad disease, right? So given that, we might be more inclined to say, you know what, we're willing to take more risk on telling people incorrectly that they might be at risk than we are in missing it. But it's going to be very context dependent. So please give that some thought when you're doing these binary classification problems. All right, so that is pretty much all of the material that I wanted to cover. So this has been a rather lengthy video, right? So we're sitting at about an hour and 47 minutes, but we've covered a lot of ground, right? So we've done everything from reading in a data set. We generated some basic plots all the way at the beginning, right? Just seeing if we could say, can we visualize the impacts that these various features might have. We looked at correlation. We fit a lot of different models in scikit-learn, talked about test train splits, grid search, and then ended up here at how we can look at those probability thresholds. So pretty extensive treatment, although we did not go into any type of detail on specific models. That was not the goal. The goal was to show you kind of like, an end-to-end look at this process, how you can easily interchange models and kind of think through things using scikit-learn. So hopefully those of you that make it to this point have found this to be helpful. And again, in the future, there will be additional videos on this playlist. Not all of them are going to be, end-to-end analyses related to like, machine learning or artificial intelligence. I plan to maybe do some stuff about, networks, graphs, because that stuff interests me as well. But this will be the format. So they're going to be long format videos. We're going end-to-end, kind of really talking through some things. And hopefully they will be useful to someone out there. All right, so with that, I am out.